Hey guys, welcome back. Today we are in chapter 13.4. We're talking about impact, and the thing about impact that we need to know is that there are several equations that we're going to need, lots of unknowns, so it made sense to talk about where they come from. So this is impact in its simplest form. So we've got particle A, particle B, they're going along. Particle A is moving faster than particle B. They collide, and after the collision, they are going along with new velocities. So let's find an equation. So starting with the equation of impulse, let's look at particle A. So for particle A, what do we have? At this position, we have MA, VA, right? And then we have FDT. And if you just, let's see, we need a positive direction, don't we? Let's call this direction positive. Okay, then from the point of view of particle A, the impact is actually going to slow it down, right? So this is a negative impact, negative impulse. So minus F dt, and that's going to equal ma v prime a, right? So rather than the 1 and 2, let's call it called a velocity after impact prime. Similarly, for B, we start with mBvB. Then we have our impulse, FDT, and that is, note, this is the same impulse, the direction is just reversed, right? So we would think of it like some sort of a force. This would be minus FDT, and this would be plus FDT. And coming back to this, it's going to be equal to MB V prime B. Right? So if we add these together, we get our first equation. So MAVA plus MB VB, when we add these together, we get 0. So this is equal to MA VA prime plus MB VB prime. Right? And we call this the conservation of momentum. So let's put this over here. VA prime plus MB VB, excuse me, MAVA plus MBVB equals MA VA prime plus MB VB prime. Right, super simple. That's an easy equation. All right, so that will get us one unknown in this situation. Unfortunately, we end up with lots more of them. So let me get rid of this. And it turns out that this is not actually how impact works, right? They don't just come together and then break apart. There's actually several steps. And so if we expand this, then what we get is that in the middle, we get, I'm going to do my best here to draw this. Right, there's a little bit of deformation there. Okay, and then we get this, like we had here, and this, and they're not to scale, obviously. I just want to emphasize the center one apparently. K and AB, right? So what we could say is that it actually follows this pathway here, right? And so if we expand the center, then we get there's VA, VB, then they make contact, then there's this period, and this period here is called the period of deformation. And this period here is called the period of restitution. And the fact that I'm writing this down means that you should be too. There will be a test, right? Okay, so this is a period of restitution. That is a period of deformation. These are actually impulses, right? So when we think of the impulses, turns out that we have two of them. And in the middle, so we have VA, VB, V prime A, V prime B, there's a velocity here, and we'll go with this direction. It doesn't actually matter what direction it is, but this we call a U, right? Right in the middle, they're hugging, they're traveling together, and then they break apart and their velocities become distinct again. So the period of deformation, we represent this as P dt, right? And the period of restitution, we represent as R dt. So the, let's see, one of the properties, because, so if you imagine an impact at, when things impact, they release sound, right? You can hear things crashing together, which means that there's more energy here than there is here. And by extension, one of the rules of physics is that the period of deformation is, and the impulse during, so this is an impulse, the impulse during the period of deformation is always greater than the impulse during the period of restitution. And the way that we consider these is we create this coefficient of restitution, E, and E we define as the impulse during the period of restitution divided by the impulse during the period of deformation, right? And so by extension, E is always going to be less than or equal to 1. And we say less than or equal to, really we mean less than, but sometimes we consider special cases where the coefficient is 1, and that allows us to do some things. So what does this mean? Well, if we go back to the impulse, this idea of impulse, then for A, right, so let's, do we have room? Can we see the, yeah, sure. All right, so for A, then we have two periods to consider, right? So we have MA, VA, plus, then we have BDT, and that's going to equal I'm just going to say MA here and U, right? And for the second one, then we have MA, U plus R dt, and that's going to equal MA VA prime, right? So if we rearrange these, then we can get that the period of restitution, right? So PDT is equal to MA U minus VA, and similarly, RDT is equal to MA, what are we at here? V prime A minus U, right? Simple step. So substituting these, so here it's clear that the velocity or the masses are going to drop out when we put it into this form. So we do the substitution and we get that for A, we just add it on here, and we can say that this is V prime A minus U over U minus VA. Okay, and this is valid for the A particle, right? And so when we do this for both particles, then it comes together and we get a reversal of signs. And what we ultimately arrive at is that when we consider both particles, then this is V prime A minus V prime B over VB minus VA, right? And the way that we commonly write this is that VB minus VA times the coefficient of restitution is equal to V prime A minus V prime B, right? Which is another relation that we need. And so this is our second equation. Right, so let's add this over here. We'll say V in E times VB minus VA equals V prime A minus V prime B, right? And something to notice is that here we have B, A, B as our subscripts, right? Well, you can reverse them so that you get A, B, B, A. The important thing is that the order here, so you got B, A, then A, and then it reverses A, then B. That order is important. So you can arrange this in either direction, depending on how you write the equation, but the important part is that they're reverse on the left versus the right side. So this is, these are the equations from direct impact. And now let's talk about oblique impact and see if we can figure out what that means. So back to this, the scenario here is that things are intersecting or things are impacting along a single axis, right? So let's consider this, okay? And here we have A and B, and they are impacting. So in this situation, it makes sense to start thinking about coordinates. And it turns out that the coordinates are pretty familiar, and that is pretty sad. Let me start over there. That the coordinate actually goes through, it's supposed to go through the middle, right? Let's see if we can do this a little better. Okay. All right. Okay, so again, this is A, this is B. Okay, and they are colliding. So in this, for now, let's just call this VB, and we'll call this VA. And let's define some things. So the cross lines here are actually coordinate axes, right? So this is our t-axis. This is our n-axis, so normal and tangential. Normal to the lines. This is called the line of impact. This is called the line or plane of contact. I always call this guy the tangent line. Makes the most sense. In the game of pool, there's the targeting line and the contact line. As long as we're clear on what these mean when we're analyzing it, doesn't matter what we call it, but that's what they're called. Other terms, the direct impact is when the velocities are aligned along the line of impact. Oblique is when they're not. It's really that simple. Let's see, what else? When we analyze this, we looked at direct impact. Let's look at oblique. So let's say that we've got something like this, right? Okay. So, one second, looking at my notes. All right, so there's actually, I like to say there's 3.5 equations because what we can notice, and then let's make this oblique as well, why not? Let's just say that VB is here and maybe there's some angle theta and some angle alpha, right? So what this implies is that there are 2 components, right? There's of each. There's the velocity in the normal and the tangential direction. So what we can say here is that VA is the sum of VAT plus VAN, right? And if these are vectors, then we can just note that they are components, right? Or, you know, we can decompose it in the ways that we're familiar with. So the previous analysis that gave us this coefficient of restitution noted that there is a period of deformation followed by a period of restitution. Well, those are specific to the normal direction, right? Right. So we could actually just add n's to this first equation, right? Where we are conserving our momentum in this direction, right? We can treat the normal direction like this. Similarly, we can also treat the normal direction like this, which alludes to what happens in this tangential direction. Well, it turns out that there is no energy exchange in this direction. So what that means is that MA VA in the tangential direction is equal to MA V prime A in the tangential direction, right? And the masses drop out, and this is our equation, which is super handy because that means that once we know the component of this guy in the tangential direction just by decomposing, then we don't have to think about it anymore, right? The only things in the normal direction are changing. So the way we write this is VA and they like to put parentheses around it. I don't have any issue with that, so why not? VA prime in the tangential direction, right? So the velocity, the momentum is conserved per particle, so then by extension, so is the velocity, right? So if we were to do a problem like this, okay, so we have this example problem, and we are given that identical balls, A and B, impact each other. They're frictionless, and they have a coefficient of restitution of 0.9, and we are asked to find the direction and velocity of each ball after the impact, right? So we need coordinates. So let's do a free body diagram and decompose these vectors. So we have VB, VBT, and VBN. Okay, and let's see, what are those? VBN is going to be the cosine of 60 degrees, which is 1/2, so this will be 20 feet per second. Okay, and this will be the sine of 40 times the sine of 60, and that is 34.641. And similarly, VA, T, so VAT is 30 times the 30 feet per second times the sine of 30, that's 1/2, so that is going to be 15. And here, 30 times the cosine, so 30 times 0.866 is 25.98. Okay, and that is VAN. Okay, and right, so with that we can do the analysis. Well, let's do the easy part first, and that would be in the tangential direction. Okay, so in the y direction. All right, and we know that the velocities are conserved, right? So VA, we say T is equal to VA prime T, which is 15. Similarly, VB T is equal to V prime B T, and that is 34.641. Okay, now in the normal direction, things get a little bit different. So we can start with this equation here, the conservation of momentum. We'll go ahead and drop out the velocity or the masses because we know that they're equal. So we'll say VA, this is n direction, VA plus VB, and maybe it makes sense to put the subscripts here just so that when we put them back together, we don't get confused about this. So VA n equals VA prime n plus VB prime n. Right, so we're going to add these up. We need a positive direction that's to the right, so this is 25.98 minus 20 equals this. So 5.98 equals B prime A n plus b prime b n. Okay, that's one relation. We have two unknowns, so we'll need two equations, and we have this one. So again, in the n direction, we're given this, so 0.9, and we're subtracting now, so it doesn't matter which one we do. We can say, let's see, we're ending with a and b, so we're ending, let's do this one. So VB is minus 20 minus 25.98, right? And that's going to be equal to b prime a n minus b prime b in the normal direction, right? And the subscripts, again, that's just talking about the direction. So let's see, what do we got? 0.9 times minus 20 minus 25.98. That is minus 41.382 is equal to b prime a n minus b prime b n. Okay, so now we have two equations and two unknowns. We have a few choices on how to solve these. We can use matrix math, or we can use a substitution method. I want to show you why it's a good idea right now to make sure that you can use matrix math. This is, if we convert this to a matrix, then we put the number on the right side, right? So doing that and just running it into matrix form, we get 1 and 1, right? So the coefficient here and the coefficient there, and that's going to be equal to 5.98, right? If it helps, you can draw a line here. This represents the equal sign, okay? And 1 and minus 1, and this is equal to minus 0.382. Okay, and when we solve this, then we get, this will be 1, 0, 0, 1, and let me run that through my calculator real quick. One, 5.98, then 1, negative 1, and minus 41.382. Okay, and this gives us minus 17.701 and 23.681. Okay, so there are two reasons why I use this method, and those are that, one, it's faster, single step. The other is that this format right here, this 1, 1, 1, minus 1, comes up over and over and over again because of the way that these relationships work with each other, right? So you're always going to end up with 1, 1, 1, minus 1, and then what you're calculating here are just what's on the other side of the equation. So getting in the habit of that means that you're going to be repeating the same simple equation over and over again. So when we pull these out, what does this mean? This means that this is v prime a in the n direction, this is v prime b in the n direction. So our vectors are v prime a is going to be equal to 15. We will do this, right? 15 squared plus, I should say, minus 17.701 squared, and then b prime b is equal to 34.641 squared plus 23.681 squared, right? We run these through. And by the way, I am not going to have you do this. As far as I'm concerned, we could report V prime A like this. We'd say VA prime is equal to 15, and this is in the tangential direction, and then minus 17.701, and that is in the normal direction. Right? This is fun. We can run through here. Then we would get that, get the values, then do that. Let's go ahead and run those calculations. Okay, so this is 23.202, and that's feet per second. And the next one, this is 1 squared plus 23.681 squared, and it's going to be equal to 41.962 feet per second. You push that number in, right? 34. Yeah. Okay. All right. So, because so there's a transfer of energy, right? So relative to the line of impact here, the trajectory of A was more toward the was closer to the line of impact, and so it transferred more energy across, right? So the net energy of the exchange was that energy went from A to B, right? Because we can see that because the velocity of A before impact was 30, the velocity after is 23. Similarly, the velocity of B before impact is 40, the velocity is 42 after impact, right? And then the angle is simply a matter of recognizing or using the inverse tangent, right? And when we run that, we get that VA is, this is 40.3 degrees, and VB, this angle here, is 55.6 degrees, right? And that is our solution. Again, it's almost always going to be just fine to report it this way, but in this case, it is good to see how the energy transferred. So I hope to fill in the blanks, and I will see you in the next video.